Hello, good day I bid to everyone. I am Aina from Group 15. Me, together with my dearest groupmates, Aiman Akila, Najwa Majid, Sarah Anissa and also Whitney, will present our design for Group 3 base oil production plant. Before we proceed further, this is the overview of our presentation today. The timestamp for each parts are also displayed so it will be easier for you to move between sections. So now, let me pass the screen to Aiman Akila.
Hi, I'm Aimal and I'll be presenting the market analysis for current demand and price for lube oil Group 3 and 3 plus. The driving forces behind the production of lube-based oil are transportation 53%, industrial sector 27%, aviation 7%, greases 3%, and lastly processed oil 10%. According to Klein 2016, the demand for Group 3 and 3 plus base oil was 4.26 million tons per year. That represents 12% of the global base oil demand, and it is expected to increase by the year 2020. The price for base oil varies according to its viscosity. Stated here that the highest viscosity, which is 8 centistokes, has the highest price, which is $785 per ton, and is the highest compared to all of the viscosity 6 centistokes and 4 centistokes base oil. There are two factors that influences the location of our plant, which are cost factors and non-cost factors. Cost factors comprises the cost for transportation for product distribution and raw material procurement. Non-cost factors represents 30% to 90% of the total operating cost. These are the example of the factors that we have taken into consideration, and from the three potential locations that we have chosen, we decided to go for Sungai Udang, Melaka. Sungai Udang poses a few elements that have some leverages during the site selection. First, it has the shortest distance, which is 6.7 kilometers to Sungai Udang Seaport and raw material supply. It also has the nearest location to hospital, which is 94 Hospital Angkatan Tentera Sungai Udang and Fire Rescue Team, Tangga Batu Fire Department. Aside from having interesting taxation incentives that could promote to our expansion, it is also the least impacted location during typhoon season compared to Korea and China. Both public school, sekolah rendah and sekolah menengah kebangsaan has the nearest distance to the Tangga Batu community. This would provide convenience for our employee. The last element that is sometimes was overlooked was that this location offers least to no language barriers between employee, as Bahasa Melayu is the mother tongue for most of the employee and they all uses English as second language. This is an important underlying cause to ensure the safety of our plant operation. That's all from me. Thank you.
Thank you, Aima Akila. Assalamualaikum and a very good day. My name is Najwa binti Abdul Majid, and now it's my turn to present about the process screening of our project. There are three main sections that I will be explained in this process screening part, which is the first one is the purpose of each process unit, followed by the comparison between the two technologies for every process unit, and the last one would be the overall selected alternatives route. I would like to begin my presentation with the purpose of each process unit. Prior to manufacture the desired loop-based stock of Group 3, there are two primary refining technologies, which are the modern technology, which is through the hydroprocessing route, and the conventional technology, which is through the solvent refining route. Both technologies include the basic steps of viscosity index upgrading, de-waxing, and finishing with the same purpose, but their mechanisms are quite distinct from each other. For hydroprocessing route, the crude oil will enter the hydrocracking unit and followed by the catalytic de-waxing unit, and hydrofinishing unit will be the last process unit for this route. Meanwhile, for the solvent refining route, the solvent extraction unit will be the first process unit prior to enter the solvent de-waxing unit, and the finished product will be treated by the clay treatment unit. Each process unit for both technologies have the same purposes, by which the first process unit of hydrocracking and the solvent extraction unit will help to increase the viscosity index up to the desired viscosity index, removes the sulfur and nitrogen as it may poison the catalyst in the dewaxing and the finishing unit, and to saturate the aromatic compounds. As going through the treating unit, the wax has potential to form when the product is chilled. Hence, the wax is removed either physically or chemically in order to reduce the pour points of the base stock in the catalytic or solvent dewaxing. The finished product will be treated by the hydrofinishing or clay treatment unit to remove the residual of all polycyclic aromatics and help to improve the color and the oxidation stabilities. In this part, I will briefly explain on the comparison between both modern and conventional technologies for each process unit. In our project, the viscosity index upgrading unit of Unit 100, the solvent extraction unit able to remove around 50% until 80% of impurities, while the hydrocracking unit consists of two interchangeable hydrotreating and hydrocracking units that help to remove the sulfur and nitrogen by hydrogenation reaction, as well as breaking the long hydrocarbon chains and the ring opening by carbon-carbon cleave prior to enter the dewaxing unit. The second point of viscosity index upgrading, as we can see, the hydrotreating and hydrocracking unit of modern technology able to increase the viscosity index up to the desired viscosity index of 120 for Group 3 loop-based oil. This would be the preferable technology that can be used to produce the base stock. The solvent has been used in the conventional technology of solvent refining, while the loop hydrocracking units use the catalyst base that helps the hydrogenation reaction to occur, and thus no solvent recovery unit is required for modern technology. The second process unit would be the Unit 200 of dewaxing unit for solvent and hydroisomerization unit. In the solvent dewaxing unit, the solvent of methyl ethyl ketone or toluene and the methyl ethyl ketone or methyl isobutyl ketone have been used to remove the wax from the solution of dewaxed oil and solvent by filtration. Meanwhile, the long-chain paraffin, which is known as the wax of hydrocarbon, is isomerized by zeolite and molecular sieve with at least one noble metal catalyst to form more branching in the molecular compounds. The solvent dewaxing unit comprises of filtration, crystallization, and solvent recovery unit, while there is one and only isomerization process involved in the hydroisomerization unit of modern technology. The finishing unit would be the last process unit for both solvent refining and hydroprocessing routes. As we can see, both of clay contacting treatment and hydrofinishing finishing units have the same purpose of removing the aromatics and the polar compounds as well as to improve the color and stabilities of the finished product, but by using the different materials and methods. The fine bleaching clay or mixture of clay with an acid has been used for neutralization of base stock at medium operating temperature, while the hydro finishing unit used the noble metals or mixture of noble metals catalyst at higher operating temperature as compared to the clay contacting treatment. After going through the comparison and purpose of every process unit of two different technologies, there are four alternative routes that have been proposed, which comprises of hydroprocessing route, solvent refining route, and combination route with different sequence of process units. As many aspects that have been compared and evaluated in terms of advantages or disadvantages of every process unit for each alternative route, the hydroprocessing route has more advantages which are able to produce the Group 2 and Group 3 base oil, high-value byproducts, environmentally friendly, no slag wax formed, high purity and chemical stability of base oil, while consists two disadvantages of high operating conditions and hydrogen as well as catalysts have been used in every process unit. As we can see, the solvent refining route have more disadvantages and less advantages as compared to the hydroprocessing route. With respect to this matter, the hydroprocessing route has been selected as the overall alternatives route for this project. That's all for process screening part. Sarah Anissa will continue with the process flow diagram.
Hi, my name is Sarah, and I will now continue with the process flow diagram. This figure shows the overview of the process flow diagram of our plant. Feedstock from the vacuum distillation unit will enter the first unit, which is Unit 100 VI upgrading unit. Then the waxy hydrocrackate from Unit 100 will enter Unit 200, the dewaxing unit, to produce dewaxed oil. And lastly, it will go through Unit 300, the finishing unit, to produce the desired product, which is Group 3 base oil. Upon designing the plant, a HAZOP simulation was also developed in order to obtain the production capacity and viscosity index of the base oil. From the simulation, we were able to obtain a production capacity of 1.87 million ton per year and a viscosity index of 243.17, which satisfies the product specification of having a VI index of more than 120. Now, we will proceed with the first unit, which is Unit 100, VI upgrading unit. The feed from the vacuum distillation unit will enter Unit 100. The feed is mostly made up of the vacuum gas oil, or VGO, that contains hydrocarbons with carbon number typically ranging from C25 to C70. It also contains impurities such as nitrogen, oxygen, carbon dioxide, and sulfur. The feed will first be heated with hydrogen before entering the loop hydrocracker reactor. In the reactor are 4 beds of zeolite catalyst and is operating at 393.3 degrees Celsius and 1300 kPa. There are a few reactions inside the reactor, which includes hydrodesulfurization to remove sulfur, hydrodenitrification to remove nitrogen, aromatic saturation, and hydrocracking reaction for the upgrading of viscosity index. Then, the products from the hydrocracker will enter the distillation column to separate the product, which is the unconverted oil, and byproducts according to its cut points. The unconverted oil will be sent to the dewaxing unit for further refining. Next is Unit 200, the dewaxing unit. The unconverted oil from the distillation column will now enter the hydroisomerization dewaxing reactor. Just like the feed into the hydrocracking reactor, the feed to the hydroisomerization reactor will also be heated with hydrogen before entering the reactor. The reactor consists of 4 beds of ZaSM5 catalyst and is operating at 355.7 degrees Celsius and 1300 kPa. The reaction that occurs in the reactor to remove wax is the isomerization reaction, where long paraffin chains will be converted to branched paraffins, also known as isoparaffins. Then, the dewaxed base oil will be sent to the hydrofinishing unit. Now we will proceed to the last unit, which is Unit 300, the hydrofinishing unit. The hydrofinishing reactor in the hydrofinishing unit serves to stabilize the product, as the dewaxed base oil still contains some residual aromatics. The feed to the reactor will once again be heated with hydrogen before entering the reactor. The reactor consists of two beds of MAXAT catalyst and is operating at 243.3 degrees Celsius and 1300 kPa. The reaction that occurs in the reactor is the saturation of the residual aromatics to convert them to naphthalene. Thus, after stabilization of the base oil is done, group 3 base oil is produced with a viscosity index of more than 120. The following is the process flow diagram of the plant before heat integration. And here is the process flow diagram after heat integration. Now we will proceed with the comparison of utilities consumption before and after heat integration. So there are two units that are involved in the heat integration, namely Unit 100 and Unit 200. From this table, we can see that for Unit 100, there is 36.09% reduction in utilities consumption after heat integration, while for Unit 200, utilities consumption is reduced by 29.44% after heat integration.
Okay, done with process screening and process flow sheeting. So let's carry on with the manual mass balance. The purpose is to compare our calculations with the values obtained from HAZOP. So the basis of our calculation is to achieve 80% conversion as mentioned in Lee et al.'s paper. Thus, looking at the overall process, we calculated that we should obtain 190 tons of base oil when 237 tons of VGO is fed. However, HAZOP shows higher yield at 213 tons per hour, which makes our overall error is around 11%. And as we evaluate at each of our reactors, the calculation errors range between 0 to 11%, which is acceptable. Moving on to the control strategy. So process control is implemented to maintain desired operating conditions in a system, and as mentioned by Nolan, process control is important as it deals with process upsets and it executes emergency actions to bring back the system to an ideal conditions. The few of many control strategies are feed-forward control, feedback control, and also cascade control. So looking at Unit 100, which is the Viscosity Index Upgrading Unit, Cascade Controller has been implemented to maintain the liquid level in distillation column C101 by manipulating the bottom outlet flow rate. While in Unit 200, our dewaxing unit, in order to maintain the reactor R201 temperature, a feedback controller is used to manipulate the hydrogen quench flow rate. And last but not least, in Unit 300, a feed-forward controller is implemented to control pressure in our gas separator C301 by manipulating hydrogen gas outlet flow. So with that, a piping and instrumentation diagram has been drawn using Microsoft Visio according to the process control strategy that has been implemented. Thank you.
HAZOP studies are conducted on our plant design to perform risk assessment and process hazard analysis. There are 3 different nodes in this HAZOP, which is Node 1, Node 2, and Node 3. So this is the process flow diagram to show the HAZOP conducted for Node 1. The Node 1 are included with the hydrocracker, inlet to hydrocracker, the hydrogen quench gas stream, and hydrocracker outlet streams to heat exchanger. Whereas the Node 2 includes the heat exchanger, feed to the furnace stream, hydrocracker unit outlet stream, and inlet stream of the high pressure separator. At last, the Node 3 covers the whole distillation column network. Next, this is the sample of our complete HAZOP that have been carried out for Node 1, Node 2, and Node 3. So this is the parameters of HAZOP which apply to our plant design intended are temperature, flow, pressure, and level. Other than that, plant layout is also being designed using the Adobe Illustrator. There are 4 parts of units in this plant layout, where Unit A is the process unit, Unit B is the utilities and offsites, Unit C is the non-plant buildings, and Unit D is the gates. Thus, the non-plant buildings are located far away from the process plant site for safety consideration. Furthermore, the economic potential evaluation of the plant design has also done to determine the economic feasibility of the plant. At first, this table shows the annual price of raw materials and products. The flow of the components is obtained from HAZOP simulation, whereas the price of each component is obtained from sources as stated on the price preferences section. After both of the information is obtained, the total price of the components per year are calculated. Apart from that, it is also assumed that the plant tariff category is under tariff E3, which is a high voltage industrial tariff. And the price of the electrical utility during peak period and off-peak period are 33.7 cents per kilowatt hour and 20.2 cents per kilowatt hour respectively. Then the total electrical cost and other utility is calculated for before heat integration and after heat integration. The electrical utility usage is collected from the HAZOP simulation, while the water and fuel utilities are collected from the heat integration calculations. Furthermore, this is the economic potential evaluation of our plant. EP1 is obtained by subtracting the total product revenue with total raw material cost and obtain 2.74 billion ringgit Malaysia per year. As for EP2, before heat integration, the EP1 is subtracted with the total utility cost before heat integration and obtain 2.727 billion ringgit Malaysia per year. Thus, for the EP2 after heat integration, the EP1 is deducted with the total utility cost after heat integration and obtain a 2.73 billion ringgit Malaysia per year. The main objective of this project was to design a process plant to produce Group 3 or Group 3 Plus base oil from the feedstock of the vacuum distillation unit in the petroleum refinery, based on the API, which is the American Petroleum Institute classification. By achieving this objective, a hydro-refining plant consists of 3 processing units, such as the viscosity upgrading unit for removing aromatics and increased viscosity index of base oil. Next, the dewaxing unit for converting waxy oil into wax-free product, and finishing unit for improving the color and oxidative stability of base oil. Next, the production and economic potential analysis were also conducted, where the plant is expected to generate 1.87 million tons of Group 3 base oil annually and produce a Group 3 base oil with viscosity indexed of 243.17. Furthermore, the total profit of the plant before and after heat integration are expected to be approximately 2.73 billion ringgit Malaysia annually. Thus, this indicates that the plant can potentially produce quality Group 3 base oil that can achieve the required product specification, and it is highly sustainable as well as economical feasible.